Hi guys, no live lesson today. I need to be in school, so little pre-recorded one. Not too complex today. Hopefully you should be able to work through this all right. So we're going to look at finite state machines. Finite state machines, or specifically a finite state automaton, which is a type of finite state machine, is another way of expressing a regular language. Last lesson we looked at regular expressions. Regular expressions are one way of expressing regular language. Finite state machines are another way of doing it. A regular language is anything that can be expressed using a regular expression. So something like the valid binary for a particular thing. So if it has to be exactly 8 ones and zeros, we could express that as a regular expression. There's possibly a more efficient way of doing it, but it'd be something like etc. and do that 8 times. So that's a way in a regular expression of saying whether something is a valid binary 8-bit binary string. Have 8 of those. As long as you follow that expression, it's going to be accepted. And anything that can be expressed using a regular expression is called a regular language. There are things that can't be, and we'll look at those later because there are other systems for doing things that can't be expressed with a regular expression, but an awful lot of things can. So as well as regular expressions, finite state automatons can be used to express regular expressions. And one of the things you'll be asked to do is to interpret or draw finite state automatons and convert between regular expressions and finite state automatons. So let's have a quick look what they are, first of all. Now this should be familiar to most of you because this is what I did for the taster session back when you guys were in year 11. So this should be fairly familiar, and for some of you it might just be a quick recap, but I want to do it again because it's been a while since you guys were in year 11 and we need to make sure we remember it, and we didn't do conversions that time. So a finite state automaton is a specific version of a finite state machine, and a finite state machine always is confusing when we start using the word machine in this context. It's not a mechanical device, it's not something with cogs and gears, it's not even an electronic device, it's a conceptual model. It's anything that follows a set of rules and procedures that are easily defined. A finite state machine is a specific type of machine which many devices and processors can be described with. So let's look at an example that will help us to begin with. We'll look at traffic lights. I'll talk about it first, then we'll draw one and you can see how it works. So a process can be a finite state machine if it can be defined in the following way. So can it be described as having a finite number of states? A state is just what condition it's currently in. You define what those states are and you have to be able to say at any given time, this model, this conceptual device is currently in this state. Now it's in this state, now it's in this state. Whatever states are defined, you can tell which of those states it's in. And it changes from one of those states to any of the other states using an input. Now it may not be possible to go from every state to every other type of state. We say if you are in this state and you get this input, you will move to this state. If you're in this state and you get this input, you will move to this state. And that's how a finite state machine works, and an awful lot of real-world applications can be defined using a finite state machine. It's a form of abstraction. So if you think of a traffic light system, you think that an individual traffic light on a pole, its states can be defined as red, amber, green and red amber. Those are the 4 states that traffic light can be in, and its inputs are just timers. So a certain timer will trigger the transition from red to amber, and then another timer will trigger the transition from amber to green, and then another timer from green to red amber, and then from red amber back to red. And those timers will be different for each one of those, and it's not possible, for example, to go straight from red to green. So there is no input that will take it from the red state to the green state. And we would express that in a diagram representation. So FSMs are usually depicted using a state transition diagram. Each state is depicted as a circle and arrows show the transitions between them. So this made up one, this isn't the traffic light, we'll look at the traffic light in a second. So this one here, it's in state 1, then whatever input A is, be it a timer, a button press, a sensor, something or other that can trigger something to happen, will then make something happen and the machine will be in state 2. If it then receives input B, it will be in state 3. From state 3, it's got two options of where to go. If it receives input D, it will return to state 1. If it receives input C, it will return to state 2. And then state 2 will only listen for input B. If it's been state 1, it will listen for input A. If we look at that in a real world one, so how would our traffic light work? It's a very simple diagram. It's just this. So I've actually expanded this a little bit more. So we're in the state flashing man and flashing amber, and it'll stay there for 5 seconds. So after the 5-second timer is triggered, as in it's run down to 0, it will move to the state red man and green light. After a button is pressed, so this is a crossing version of a traffic light, it will then move to red man and amber light state with a 1-second timer being started, and when that 1-second timer counts down and triggers, it will move to the state green man and red light. It will then stay there until the 10-second timer counts down and triggers it, which will move it to the state flashing man and flashing amber, and that will keep running indefinitely. And that's a model, a conceptual model of a Pelican crossing traffic light system. It's not perfect. You probably want to expand it a little bit. So there might be something to do with a sensor that detects how heavy the traffic is and waits for a lighter time. So there'll be a state waiting for light traffic that it might move to. And when that traffic sensor detects there's no cars coming, then it'll move to the state red man and amber light, or however you want to move it. I haven't in this included a few other possibilities like the flashing amber. Oh, I did include flashing amber. But you could expand this. You could keep making it more complex by adding more possible states and more transitions between them. But ultimately, the vast majority of systems we would like to make could be represented using this finite state machine system. Right, we're not going to do this task just yet. I want to get onto Automaton, so we're not going to look at that just yet either. But yes, I will look at this one. So an extension of a finite state machine that just takes inputs and moves between states is the idea of a Mealy machine. This is the same as a standard machine, also referred to as a Moore machine, but each transition has an output as well. So as we run through a finite state machine, there is an output being generated. And in a lot of applications, things make an output. So this is a way that these things can be modelled. So if we look at this one, I'll sort of step us through this. This is a Mealy machine that accepts a binary string as its input. So it's going to take as its input this first one, 0, 0, 1, 0, 1, 0, 1, 0. This arrow here means this is where we start. So when this machine begins, we are in state 0. Now our first value that is input is a 0. So from here, we look at this. That's a 1, so we're not going down that path. That's a 0, so we're going here. So this means we go from state 0 to state 2. And this pipe tells us that after that, that's our output. So because we've gone from state 0 to state 2 and our output here is a 0, that's the first part one of our outputs. Let's try that again. Yeah. So we've output 0. And now we're in state 2. So we have a look over here. What's our second input? Well, our next input, we've already done that 0. Our next input is another 0. But we're in state 2 now. So we look for an arrow that tells what to do in state 0. There it is. So if I'm in state 0 here, sorry, state 0 here, not state, input 0, we follow this arrow and remain in state 2 and output a 0. So a 0 is output, and we're still in state 2. Our next input is a 1. So from state 2, here's the transition. If our input is a 1, its output is still a 0. So a 0 is output, and we move to state 1. Our next input is a 0, which is here. So 0 moves us to state 2 and outputs a 1. So we're back in state 2. Our input is a 1. So we move to state 1 and output a 0. Now we're in state 1, our input is 0, so we move to state 2 and output a 1. We're in state 2 and our input is 1. So again, we go this way, output a 0, and move to state 1, where our output is 0. Sorry, where our input is a 0, there it is, and that will output us a 1, leaving us at the end of our string in state 2. So that is our output. Okay, so I'm going to ask you, could you pause the video and have a go at the second one using this set of inputs, so 1, 1, 1, 0, 0, 0, 1, 1. Could you start in state 0, follow this around and write out what the output would be? So pause it, I'll go through it in a second and you can see if you got it right. Okay, hopefully you paused it and you're not just being lazy and watching it. You're far more likely to learn this stuff if you have a go at it. Let's have a go at the second one. So our first input is a 1. So we're in state 0 and we go down the 1 channel here. That takes us to state 1 and our output is 0. Then we're in state 1 and our input is a 1. So we follow this one, leaving us in state 1 and our output is a 1. Then it's another 1, leaves us in state 1, our output is a 1. Then it's a 0, so we follow this arrow, outputs a 1 and leaves us in state 2. Now we're in state 2, our input is a 0, so we follow this path, leaving us in state 2 and outputting a 0. The next 0 leaves us in state 2 and outputs a 0. Next one leaves us in state 2, outputs a 0. That's a 1, so that moves us to state 1 and outputs a 0. And then we're in state 1 with a 1, leaves us in state 1 and outputs a 1. So that is our final output. So the last question down there, what is the function of this machine? Has anyone figured out what it does? Well, if that input leads to this, and that input leads to this, what it's doing is right shifting. That's a finite state machine for a right shifter. So it's taken 0, 0, 1, 0, 1, 0, 1, 0 and turned it into 0, 0, 0, 1, 0, 1, 0, 1. It's moved every bit to the right. In other words, it's divided it by 2. So there's a finite state machine representation of something that divides a binary number by 2. Okay. So that's a finite state machine. The type of finite state machine that generally gets asked about, and in the last few years it's the only type that's been asked about, is a finite state automaton, the plural of which is finite state automata, because English is weird. A finite state automaton is a Moore machine, so it's got no outputs, it's just got inputs, which has an accept state. The accept state means that if you finish your set of inputs and you are in the accept state, then those set of inputs were accepted. If you finish your set of inputs and you're in any other state, then those set of inputs are rejected. So like a regular expression, certain strings will be accepted and certain ones will be rejected. Let's have a look at an example, easiest way to explain it. So in this one, in this case, the accept state is S2. This double ring here, let's put some labels on. The double ring means the accept state. So if at the end of my string of inputs I'm in the accept state, then that string is a valid string, it's an accepted string. If I end up in a different state, then it's a rejected string. The arrow here means this is the start state. So all automatons will have an arrow pointing towards one state. Incidentally, there's nothing against you starting in the accept state. You could have the arrow pointing to the same state as the double ring state. That would be fine. So in this one, we're going to pass these 4 strings. which of those 4 strings will be accepted by that finite state automaton? I'll do a couple with you. I want you to do the rest. So first of all, A, B, B, A. Well, we start in state 1. Then our first input is A. So we follow this one. No, it's a Moore machine, so no outputs in this, so it's a lot easier. So that leaves in state 1. Our next input is B. So we travel along here to state 2. Our next input is B. So we follow here to state 2. And our last input is A. So we go back here to state 1. This is where we finish in state 1. It's not the accept state. So A, B, B, A is rejected. The second one, B, A, B. The next one, A, 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 B. And the fourth one, B, B, B. Could you again pause the video and have a quick go at these? And if you can you figure out what the rule is for this? Remember how last lesson we took regular expressions and described in words what is permitted? Can you do the same thing with this? Can you look at that finite state automaton and the strings that have been accepted and say a string will be accepted if, and describe it in words? So pause the video, have a quick go at that. I'll go through it in a few seconds. Okay, so BAB, start here, we go to B, then to A, then to B. We finish here in the accept state, that is accepted. That's weird. AAB, we start here, A, B, we end in the accept state. And BBB, we start here, go to B, 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 accepted. And the rule was that anything that ends in a B will be accepted. Now it's not on the slide, but can you think of how that exact same system could be represented using a regular expression? So anything that can take any number of A's and B's but must end with a B. Again, if you want to pause the video and see if you can do it, please do. There's no nice algorithmic way to take a finite state automaton and convert it to a regular expression or the other way around. All you can really do is look at what the rule of it is and then write an expression that follows that same rule. Okay, so in this case, we want something that ends in a B and can contain any number of A's or B's beforehand. So a regular expression for that would be something like A or B 0 or more times followed by B. That would be accepted. So that regular expression is directly equivalent to that finite state automaton. Okay. Now, a couple more bits of terminology. Each finite state automaton and regular expression has an alphabet. An alphabet is this range of inputs that are permitted. So in this one, the alphabet is A and B, because A and B are the permitted inputs. In this one, the alphabet was 1 and 0, because 1 and 0 were the permitted inputs. A valid finite state automaton must deal with every possible input for each state. No state or input combination can be undefined. So if we go back to the finite state machine, that wasn't the case. So I go back to this one. Here, we didn't need to say what would happen here if the button was pressed. That was a possible input, but it wasn't defined. In a finite state automaton, you have to define that. So that's why in this case, for example, we have the 0 looping back to itself to say we don't want anything to change if 0 is done, but it still has to be defined. So it just loops to itself to say nothing changes. We stay in this state and continue waiting for a 1, which is what would take us to the next state. Same thing in this one. From state 2, an A will take you to state 1. From state 1, a B will take you to state 2. An A and B will do, an A in state 1 will do nothing, but we have to indicate that by having the arrow pointing back to itself to say an A will do nothing, because it has to be defined what would happen if you were in this state in state 1. So if you're in this state, state 1, and got an A. Okay. So, activity. Now, on the VLE is a Java file, a JAR file, that runs a nice little program for creating finite state automatons. If you have a computer at home that is configured to use JAR files, then by all means you're welcome to use that. You probably don't. We do them because our computers are configured to use that. It's a JAR file because that visual automaton simulator was actually a project by a student, not at our school, it's a different school, but it was something they made, exported it as a JAR file, distributed it, and people can use it. It's a really, really good project. But yeah, if you want to be able to use JAR files, you need to go download the JRE. If you just Google JRE, it'll be the top link. You probably have to sign up for an Oracle account. I'm not sure if they still require accounts. They might let you just download it, integrate things. Install the JRE, Java Runtime Environment. Once that's installed on a PC, you should be able to double click the JAR file and it will just execute. So if you want to do that, you want to install the Java Runtime Environment, you may have already done it as part of your installing Eclipse, I don't know, and then download the Visual Automaton Simulator from the VLE, you can use that. If you do that, let me just grab it. So there it is, Visual Automaton Simulator. So it's just a JAR file. There we are. It will run like this. Just choose that. Yep, that's fine. Don't change anything on there. And this will appear. And you can put in states like this. You can call them anything, by the way. They don't have to be S1, S2. They can be whatever you want to call them. It can be descriptive of what they are. So put another state here. You can then use this to put transition between them. So A will transition to there. B will transition to there. B from here will remain in that state. And A from here will remain in that state. And then I can right click on this to say that's going to be the start state, that's going to be the accept state. And then what I can do, I'll set my alphabet to AB, and then what I can do is test it. So I can put in things and run it, it'll tell me whether accepted or rejected. So if I say ABBA and run it, it says that is accepted. If I put in something that ends in a B, which in this case will be rejected because only A's lead to the accept state, that's rejected. So I can actually test these things out. And if I, for example, forget a particular transition, so from here I haven't said what happens if B is the input, which has to be there for it to be valid, it will tell me that as well. You can't start the automaton because the following problem, the state S1 must have two transitions. So you can use that simulator if you want, it might make life easy, or you can just do it pen and paper if you're confident about it. I'm happy either way. I want you to create a finite state automaton diagram for each of these systems. And also, it's not on there, but you guys I think can do it. Can you also write down a regular expression for each of these as well? So finite state automaton with an alphabet of A and B, which accepts any string with an even number of A's. So it has to have two A's, or 4 A's, or 6 A's. I'll leave it up to you to decide whether you think 0 is an even number or not, because it's a slightly easier one if you accept 0 as an even number. If you want to do it without 0 being an even number, it's slightly tougher. Finite state automaton with an alphabet of A and B, which accepts any string that ends in AA. Now bear in mind, AA is not in the alphabet. So what we can't do, shouldn't have closed it, let me just get it back up again. So what we can't do is have a transition where AA is there. That's not in the alphabet. The alphabet is A and B. You can only have a transition for A and a transition for B. But it has to be A followed by another A that leads to the accept state. And then anything, one A doesn't get there. So have a think about that one, see if you can do that. An FSA with an alphabet of AB, which accepts only the exact string ABBA, nothing else. So anything else from there will take away from it, won't be able to done. This will make use of something called a sync state. There will be one state that once you get to that state, there is no escape again. So anything other than that string. So if they start with a B, it'll go to sync state. If they do an A, it will lead to the next state, but then anything else will take them to sync state, etc. That's the only way that's going to work. It has to follow A. It's to go from A to B to B to A, and that's the accept state, and anything else takes you down to state they can never escape from. And finally, a very tough one, allow an input alphabet of A, B, C, and accept any string with all 3 characters in any order and any permutation. So as long as all 3 characters have been used. So see if you can make a finite state automaton and a regular expression for each of those. I'm not going to give you the answers now. Well, at the start of next lesson, we'll go through that. So I want you to work on that, get as far through as you can. This tends to be a bit of a divider on this one. Some people look at that and go, yeah, it's this, clickety, clickety, clack, done. Some people will really struggle with it. It just depends how your brain's wired. Do your best. Okay? Right, we'll leave it at that. If you've got any questions about this, please email me. As soon as I'm in school, I'm doing the things I need to do, I will check my emails and I will respond to them. But if you're okay with it, have a go at this. Finite state automatons and regular expressions for each of those 4 scenarios.